All right, so in this problem, we've got a part A and a part B. It says, what's the highest hill that a bike can clear without pedaling if the bike approaches the hill with a speed of 21 meters per second? So I've shown this picture before where we've got, here's a level surface, then it goes up. And so we're going to have the bike at two different locations. So when it's here, we're going to have the person at the top of the hill, and then we're going to have the person at the bottom of the hill. So it says, in this problem, we know the speed that it approaches the bottom of the hill at. So we know that this amount right here is 21 meters per second. So that's my original velocity. So my original velocity is 21 meters per second. And we want to know what's the highest hill that we can clear. Well, that means that we want to completely run out of kinetic energy so that when the bicycle gets from here to here, the only energy it will have will be potential energy because we will have exhausted all the kinetic energy we have. If I were to still have kinetic energy up here when I get to the top of the hill, that means I could have gone up to a higher hill because I want all of the energy to be lost because we're looking for the highest hill that a bike can clear. So that means it has to lose all of its kinetic energy and all be potential energy when it gets there. So my equation, like it always is KO plus UO plus W equals KF plus UF. And I want to say one other thing here that I haven't said yet. You can have more than one work in the problem. Like I could have work that's causing something to speed up, but I could also have friction that I have to overcome. So it's possible that you could have like a W1 and a W2. Okay, so just be aware that this equation could involve more than one W in the solution. Now, if we look at this, we're at the low point down here. So if we're at the low point, then we can say that that's ground level and the U is 0. We're also not going to be doing any work. We're not pedaling. It says the bike is not, there's no pedaling while we're on the hill. So there's no work being done to get from there to there. So that means that the work is also equal to 0. And if we're trying to get to the highest hill, then we know that we have to run out of speed when we get there. That would get us to the highest hill. And so my equation is simply KO equals UF. So I'm going to replace KO with 1/2 MVO squared, and I'm going to replace UF with mg times the final height. Here's my equation. The masses cancel out, and I'm solving in this problem for the highest hill, so I'm solving for HF. So all I have to do is move the G down there. Well, I've got to multiply through by 2 and then move the G. So if I multiply through by 2, I'm going to get VO squared equals 2 GHF. So HF is going to be VO squared divided by 2G. So I'm going to have the original velocity squared divided by 2G. So the original velocity was 21 meters per second. G is 9.8 meters per second squared, and that will give me meters for my answer because the top is meter squared per second squared, and the bottom is only meter per second squared. So the second squares will all cancel out, but I'll have meters squared divided by meters, so my answer will be in meters. And the answer for this problem came out to be 22.5 meters. So that's your answer for part A. And then in part B, it says that the bike and the rider have a combined mass of 7 kilograms. What's the total energy possessed by the bike and the rider? So I need the mass in order to actually solve for individual energies. But I know that this is the total energy here, and that's the total energy there. So I can either take this thing and plug in 7 kilograms with 21, or I can plug in 7, 9.8, and 22.5 here, and I'll get the same answer. So if you want to check your work and see if you do get the same thing or both, you could do both of them, but I would use my original facts. So the total energy, so the energy, I don't know, I guess I'll call it energy total, is going to equal the same thing as the original kinetic energy. Because all the energy to begin with was kinetic energy, and energy is conserved. So that's just going to be 1/2 mVo squared. So it's going to be 1/2 7 kilograms times 21.0 meters per second squared. That will give me the answer in joules. That will give me joules because I get a kilogram meter squared per second squared, which is a Newton meter, and a Newton meter is a joule. And if you solve that, you get 1,544 joules. All right, any questions on that one? So let me bring it down a little bit so you can see the whole solution. All right. So most of these problems don't involve an awful lot of work. I mean,